Okay. So, how do I solve the logical XOR problem? We know, I think we had seen earlier that it is not possible to solve the logical XOR problem using a perceptron. It is not linearly separable because the values are here and here, right. So, we need to be able to figure out a way to solve the problems where the boundaries cannot be a straight line and you cannot separate the class by just a straight line. So, what is the way forward? So, in this case you add one more neuron. Okay, now it becomes a hidden layer. We have the input layer, we have a hidden layer and we have an output layer. Okay. So, in this case again there is only one, even though it is a binary class in the XOR, the single perceptron cannot solve it. So, we try to add one more neuron and see whether it is possible to solve this. Okay. So, let us use this one. Let me clear all this. Okay, let us use this network. Assume that we have already found these values of the weights. Okay, in this case the bias has no value because it is always multiplying and then by 0. So, it is not going to have any effect. So, you can ignore this if you want. Okay. In many cases, instead of having a separate bias value as we had shown earlier, it will become part of the input. So, we can consider this as x naught. So, every input will be added with the bias value. So, in this case if you use the standard computation model that we had described earlier. Okay, so, here H 1 equal to x 1 W 1 1. Okay, so, we call this as W 1 1, W 1 2, W 2 1, W 2 2. So, for H 1 the weights are the x 1 is contributing its value through W 1 1. Okay, so, that is why we have it here. X 2 is contributing the value to H 1 through W 2 1. And then the bias is contributing its value through B into W B 2, right. So, you can compute H 1 and H 2 in this fashion for every input that you are providing. Okay. So, in this fashion H 1 could be computed and then Y could be computed using, let us call this as V 1 V 2. Y is equal to H 1 V 1 plus H 2 V 2, and if you have some contribution from the bias, if it is not equal to 0, we can add that. So, in this case since it is 0, we are not going to be considering this, we can actually ignore. Okay. So, you can fill this up. So, our output would be like this, right. So, when you compute the values of this, you will see that the H 1 is translated into this form. Okay. So, H 1 and H 2 if you notice are the representatives of the input parameters, and then notice that in this case there is an input space and there is a hidden space, and this is the output that you are computing, and then it is also the expected output, right. You can notice that from the input space to the hidden space there is a change. What change that you find? The values that you have here for 0 1 and 1 0 have become 1 0 and 1 0 in this space. Okay, it is very similar to what we saw in the LSI where we used SVD, right. from the term document matrix using your, let us call this as X. So, here you have the terms and here you have the documents, right. So, this is the input space that we had given to the LSI. When you use the SVD, what happened was we have U sigma and V transpose, right. So, it was decomposed into 3 different matters, this you know. If you look at U, the number of rows in U is very same as what you had in the original matrix X, right. So, that is why we used to call the elements of U which are representatives of our terms, and then we can either truncate the U based on your sigma size, right, the rank of that, or you can leave this. So, I can have, let us say, about 50 elements and it will still represent term 1, term 2, term 3 and so on, right. And if you have more precision, have it extended to 100, or you want to have the entire precision, then you do not want to lose anything, you can keep the entire vector or the row vector, right. So, this is our embedding that we were talking about. But if you look at the actual values from the X, right, T1 used to represent the term frequency or TF-IDF values and so on for individual documents. Now, in this case, the T1 is translated into a different space altogether and no longer represents only the terms in documents, right. So, this part you understand, right. In the same fashion, if you look at this XOR, the input space is the 0 0 0 1 1 0 and 1 1. So, when you move it to the hidden domain, it is translated into 0 0 1 0 1 0 and 1 1. So, it is now has shrunk the space, right, and then those values that output 1 has been shrunk into one piece. Okay, you see what is happening here, right. So, what happens if I increase this to 1 more? So, how will this look like, right. So, try to increase the count of the hidden neuron by 1 and then see what happens to this table. Okay. You see this, right. So, now we are able to shrink the space of the input into a smaller space using H1 and H2, and we are still able to create a boundary in the space of hidden layer. So, there is a input space that you can talk about. Let me erase some of this to show you that part. So, our input space is x1, x2, we have 1 here, and then this is our 0 and we have 1, right. So, this is our input space. So, in hidden space, we have H1, H2, so what happened here? We have a 0, oops, right. 1 0 is like this, and then 1 1 is this way, correct. So, we have one value here. So, it is easy for you to now separate these two out in this space, correct. So, there is a change from the input space to the hidden space, and in the hidden space we are able to really do the boundary, rather we are able to really compute a boundary that separates these values in a linear fashion. Okay. So, for us to get to the level where there are non-linear conditions, we are going to be increasing the hidden unit, and it will depend on the size of the application. For example, in many cases when you go down the lecture series, you will find the hidden space would be around 100, 200, or in some cases it is even 500 and so on. Okay. So, I have provided all the intuition that we have spoken about in this particular slide. Okay. So, you may want to read this and then understand this cleanly. So, the last one is a question for you. I will try to answer this question.